Hi, everyone.
Welcome, sir.
It's a pleasure having you here today. The topic we are going to be looking at is centered on gas power cycles. In thermodynamics, it finds its major application in power generation and refrigeration. And any device that are engineered, any device that are set to operate to produce a network output, such device is termed as engine. And the cycle in which gas power cycle operates on is also known as what? Gas power cycle. And the working fluids in gas power cycle is majorly on air. That is the working fluid. So thermodynamic cycles are classified as an open cycle and closed cycle. An open cycle is the one in which some of the air involves continuous recirculation. That is a cycle that has initial state and tends to go to the final and come back to the initial state. Unlike the gas power cycles, which are cycles in which once it has performed its normal operation, some of the gases expel, which form in form of air to fuel ratio. They are being renewed into the cycle. Some of the areas of application of gas power cycles are the purpose of studying gas power cycle are as listed below. Number one is to understand how thermal energy is converted to mechanical work. Two, to estimate the efficiency and performance of gas-powered devices. The third one is to guide the design and improvement of engines and turbines. And the last purpose of gas power cycle is that it is used to evaluate the effect of operating conditions on output power and efficiency. Now, what are the various types of gas power cycle? The gas power cycle are broadly classified into two types, namely the air standard cycle. Air standard cycle. And the second one is real cycles. Real engine cycles. Under the air standard cycles, we have the following cycles under it. The first one is Otto cycle, which is also known as spark ignition cycle. We have diesel cycle. We have dual combustion or limited pressure cycle. The next one is we have Brayton cycle. We have Ericsson cycles. And lastly, we have the Stirling cycle. Now we have introduced the gas power cycle to ourselves. We said the gas power cycles is a cycles in which the working fluid is gas throughout the process. Then also, We did mention some of the cycles that falls under the gas cycles, in which we have the Otto, the diesel, dual cycle, Eriskin, Stalin, and so on and so forth. Then the next thing we are going to do before we start taking it one after the other, before we start analyzing each of these cycles that we have listed one after the other, is to look at a Carnot cycle. The Carnot cycle was not being mentioned in the one which I have listed. The Carnot cycle is the cycles that serve as a yardstick to measure every other performance or efficiency of the cycles. It's the most efficient among all the cycles, but in the real sense, it doesn't occur. It's an idealized cycle. Is meant as what? As a yardstick to determine the efficiency of other cycles. We want to look at the energy analysis of a Carnot cycle. Energy analysis of a Carnot cycle. A Carnot cycle consists of two major key processes. It consists of an isothermal process, and isentropic process. Isentropic process simply means a reversible adiabatic process. So from these two processes, they are also being sub-classified or subdivided into isothermal expansion and isothermal compression. The isentropic process is also divided into isentropic expansion and isentropic compression. Now we are going to consider two schematic diagrams in explaining this process that I've mentioned in the board. The two diagrams are known as the PV diagram and the TS diagram of the Carnot cycle. Now let's look at this. This is the PV diagram. It's process 1 to 2, 2 to 3, 3 to 4, then 4 back to 1. In process 1 to 2, this is an isothermal expansion process. So at this phase, T8 is constant. This is where it is being added to the system. So from process 2 to 3 is considered as isentropic expansion process. At this level, whenever they are talking about an isentropic expansion process, is a process whereby it is not being allowed to come in or go out of the system. So Q in that state tends to 0. Here's an isentropic expansion. Then 3 back to 4, we have isothermal compression. So at this level, we have TL. It's constant. And the last state, which is state 4 back to 1, we have isentropic compression process. So what happened to Q3 to 4 in that case? This is still 2 to 3, which tends to 0. Then 4 back to 2, 4 to 1 equals to 0 as well. That is the PV diagram. So this is the TS diagram. Temperature entropy diagram. So from here to here, we can say T1 equals to what? T2. Then from this side, or we can name it T1 or T2. Then from here to here, we have what? T3 equals to what? T4. So at this level, we will notice that Entropy S2 equals to what? S3. Then S1 equals to what? S4. At this point, it is being added to the system, and at this level, it is what's being rejected into the system. Now, let's now look at the energy analysis of this system. So what are the fundamental laws that we are going to use in analyzing this? It is still your first law of what? Thermodynamics, which says that whenever a system undergoes a thermodynamic cycle, the net heat transfer is the same thing as what? The net work transfer. So let's write down the summation of field cycle equals to summation of what? W. So in stage 1, we know that stage 1 is termed as what? An isothermal expansion process. At that level, you go back to your fundamental. Don't forget that put two specific heat. I put you specific heat at the constant pressure and specific heat at the constant volume. So at this level, you go back to the formula that I've already done, where we are trying to analyze heat or work transfer in an isothermal process. If you can recall, we have done something of this. W equals to P1 V1 ln V2 over V1, which is the same thing as P1 V1, which is the same thing as P1 V1 ln P1 over P2. We have done this expression before. And this expression, according to the equation of state, it can also be represented as B1 equals to what? RT1. So you can represent it as what? W equals to RT1 ln V2 over V1. So this is what we are going to use in analyzing for process 1 to 2. For process 1 to 2, process or stage 1 to 2, we call it what? Isothermal expansion process. At this level, what happens to the work done? The work done from stage 1 to 2 is given as P1, since we are analyzing 1 to 2, P1 V1, it will be P1 V1 ln V2 over V1. If you are writing it in terms of volume. If you are writing it in terms of pressure, go back to your fundamental, which is the Boyle's law, which is P1 V1 equals to P2 V2. When you make V2 V1 the subject of the formula, you have P1 over P2. So this is the work transfer in stage 1. Then go back to your first law of thermodynamics. You want to analyze that of heat, Q1 to 2. This can also be expressed as RT1 ln V2 over V1. This is for the work transfer from stage 1 to stage 2. Then for heat transfer, Q1 to 2, according to your first law of thermodynamics, says that the summation of Q equals to what? Summation of W. So at this level, you repeat the same thing you have for work transfer for that of what? Heat transfer, which is the same thing as P1 V1. Let's write this one in terms of pressure. Ln P1 over P2, which is the same thing as RT1 ln P1 over what? P2. It can also come in terms of volume. Don't forget. So this is for process 1 to process 2. Now we are still on the cycle analysis of the Carnot cycle. We have done for stage 1, which is process 1 to process 2. The next one we are moving at is stage 2, which is process 2 to process 3. And recall from the PV diagram that process 2 to 3 Now, for stage 2, which is process 2 to 3. What happened at that level? We were told that it is an isentropic process. An isentropic process is a process where the entropy is 0. And if we go back from the entropy that we did, we have entropy equals to change in Q over T. Change in Q equals to change in S multiplied by T. If you go back to the TS diagram, for an isentropic process, which is process 2 to 3, you can see that entropy 2 to 3, S3 minus S2, they have the same value. That is why Q tends to 0 at this level. So therefore, Q2 to 3 equals to S3 minus S2 multiplied by T. And S3 and S2, they are on the same vertical form. If their value is 3, for example, which means S3 equals to S2, which equals to 3. 3 minus 3 becomes what? 0. So Q2 to 3 is 0 at this level. Then what is the work transfer in this case? W2 to 3 equals to, at this level, the specific heat at a constant volume multiplied by the temperature is changing from what? Stage 3 to stage 2. It's changing from what? 3 to at this level, we go back to our first law. We analyze for work transfer. W2 to 3 equals to RT2 ln in terms of volume. V2. No, it will be V4 over V3. If I'm to do it in terms of volume, you see it now. It will now be P3 V3 ln V4 over what? V3. In terms of pressure, becomes what? P3 V3 ln P3 over P4. So this is the work transfer for stage 3. Now, what is the heat transfer? Following your first law, which is work is the same thing as what? Heat. So Q2 to 3.
So 2 to 3 or 3 to 4?
Q
2 to 2.
I'm sorry, it's 3 to 4. 3 to 4. 3 to 4. Q3 to 4 becomes RT2 ln V4 over V3, which can also be written in terms of pressure and volume as E3 V3 ln V4 over V3, which is the same thing as what? E3 V3 ln P3 over P4. Now, for stage 4, that is the final stage, stage 4, which is process
4 to 1.
4 to 1. So what happened at this stage for Q? It is referred to as an isentropic compression process. What happened? S1 is the same thing as S4. So we follow the same procedure. Change in Q equals to change in S multiplied by T. Change in Q, which means Q is changing from what? 4 to 1. So we have S4 minus S1 into bracket C. Since S4 and S4 equals to S1 in terms of value. If you look at it, therefore, Q4 to 1 becomes 0, according to what we have on the schematic on the board. Then, what happens to the work transfer at that level? W4 to 1 at the constant volume, CV minus CV into bracket C4 minus C1. That is at that level, since it is doing what? It is compressed. Having looking at the whole stages that we have, stage 1 to stage 4, which is process 1 to process 4. The next thing we want to look at is the cycle efficiency. And for any cycle efficiency that involve engine or heat pump or a refrigerator, it is always given as the net work output. The cycle efficiency is given as the net work output divided by the heat supply from the system, which is the same thing as network output. Simply means what? QS minus what? QR over what? QS. At this level, something can go out. We have 1 minus QR over what? QS. Don't forget, from the diagram, this is where it is being added. It is being supplied here. Is representing QS. And this is where it is being neglected. That is Q1 to 2. QS equals to R T1 ln what? V2 over V1. Don't forget, it's the same thing as QH. QH. Then QL equals to QR is the same thing as what? RT2 ln what? V what?
V3.
V4 over what? Over V3. Are we together? So the next thing is you want to substitute it into this formula to determine the Carnot cycle efficiency. So we go back. We have the efficiency equals to 1 minus RT2 ln P4 over what? D3 divided by what? RT1 ln what? V2 over V1. If you look at the PV diagram, you will notice that V4 over V3, when you equate it together, is the same thing as what? V2 over V1. This is what I'm trying to say. V2 over V1 equals to V3 over V4. So go back. Something is common at this level. 1, this cancels this. Everything here goes out. So you are left with 1 minus T2 over us T1. So that is the Carnot cycle efficiency mathematical representation. An alternative method in solving this. We have alternative way of solving this as well. Alternatively, go back in terms of entropy. Go to the TS diagram. Entropy is given as what? I'm sorry, Q. Change in Q equals to change in S multiplied by what? C. So Q1, this is where it is being added. It is Q1 to 2, yes or no? Q1 to 2 equals to entropy what? S2 minus what? S2 minus S1 into bracket T, which is T added to the system, TH. You can call it TH. TH. This is where it is being added. Then where it is being rejected is what? 3 to 4. So it will be what? S4 minus S3 into bracket what? TL. Are we together? So what is the next thing? You go back to the efficiency. substitute it. Efficiency equal to what? Q1 to 2 minus Q3 to 4 over what? Q1 to 2. So this is the same thing as 1 minus Q3 to 4 over what? Q1 to 2. So the efficiency becomes in this 1 minus 3 to 4, S4 minus S3 multiplied by TL over what? S2 minus S1 multiplied by TH. So S4 and S3, look at it. This thing is not something that just came down from heaven in abstract form. If you look at diagrams, since we engineers communicate to ourselves through diagram, look at F3 and F2, are they not the same thing?
Yes, sir.
S4 and S1, are they not the same thing?
Yes, sir.
So which means they are equal in values.
Yes, sir.
Yes or no?
Yes, sir.
So this thing can easily go up. S4 is the same thing as what? S1. S3 is the same thing as this. So this gentleman goes. So we have the cycle efficiency equals to 1 minus TL over what? TH. Don't forget that your TL is the same thing as T2. And TH is the same thing as what? T1. Example 1 on Carnot engine. A Carnot engine working between 500 degrees Celsius and 30 degrees Celsius produces 120 kilojoule of work. Full stop. Calculate the engine thermal efficiency. 2. The heat added. And 3. The entropy changes during its rejection process. Now, solution. Step 1. The given data. It is added T8 at 500 degrees Celsius. TL is 30 degrees Celsius. 500 plus 30 gives 500 plus 273 gives 773 Kelvin. And 30 plus 273 gives 303 Kelvin. So what else are we given? Heat is added. Is it heat that is being added or work? Work. The net work output is 120 kilojoule. Which is the same thing as 120,000 joule. So the next step is to define unknown. Fine. We are asked to determine
Engine thermal efficiency.
we are asked to determine one, the engine
Thermal efficiency.
the thermal efficiency of the engine. What again?
Heat added.
The heat added, Q8, and what? Entropy change at where?
During the rejection.
The entropy change at where it is being what? Rejected. So that is S3 minus S4. So the next step is step 3, assumptions. Assumption 1, air is modeled as an ideal gas. The second assumption, the kinetic energy and potential energy effects are negligible. Those are the two assumptions that we can bring out of the question. The next step is step 4. Bring out a schematic. Represent both on PV and what? TS diagram. Since it's a Carnot cycle, it involves what processes? 1 to 2, 2 to 3, 3 to 4. At this level, we have QH and temperature H is constant. Q2 to 3 becomes 0. Then at this level, we have TL equals to C and QL. And the final state, we have Q forms to 1 equals to 0. That is the PV diagram. Then for the TS diagram, it is being added at temperature T1 and it is being rejected at temperature T. So this is the schematic, the PV diagram. And this is the TS diagram. So the next step is to write out the governing equation, which is step 5, governing equation. So the first one is the engine thermal efficiency, which is 1 minus T2 over T1. The second one is the network output equals to Q supply minus Q rejected. And the third equation is entropy S3 minus S4.
X4 minus S3.
Entropy S3 minus S4 equals to QL over TL. Now we want to begin to start analyzing the problem by solving. The first thing we have to do is to determine the thermal efficiency. From this expression, we have the thermal efficiency to be 1 minus T2 over what? T1. And T2 is given as 303 and T1 is given as 773. So which is the same thing as 1 minus 303 divided by 773. And the answer becomes 0.608, which is the same thing as 60.8%. That is the thermal efficiency of the engine. The next one is to determine the heat added to the system. QH. Now, let's go. The thermal efficiency equals to the net work output divided by what? QH. So when you make QH the subject, QH equals to the net work output divided by the thermal efficiency. Now plug in the values into this equation. So we have the net work output is given as 120,000. 120,000 divided by the thermal efficiency, which is 0.608. So what is the answer?
197,000.
197,368.
368.42.
Which is equivalent to 197.4 kilojoule. So the next thing, which is the third one, is to determine the entropy change at where it is being rejected to the system. So which means we need to determine QL before we can determine the entropy. So going back to network output expression, network output equals to QH minus QL. Taking this here, QL becomes the net QH minus the net work output. So now let's plug in the values. QH is calculated as 197,368 minus the net work output 1,220,000, and the value becomes 77.368. That's good.
Yes.
Which is the same thing as 77.4 kilojoule. Now we can now determine the entropy change at where it is being rejected. Therefore, S3 minus S4 equals to QL over what? TL.
Yeah.
So QL is determined as what? 77,368 divided by TL is calculated as 303. 303. Now the answer becomes S3 minus S4 equals to 0.25534
5534
kilojoule per Kelvin. So we have come to the end of the solution of the Carnot problem. We need to go back to the gas power cycle now. We are starting with the Otto cycle. The Otto cycle simply means SIE engine, spark ignition engine. Before we go into the energy analysis of Otto cycle, we need to unravel, or I need to introduce you to some of the terminologies that are used in engine. Our own major concern, I'm not here to teach you anything on automobile, but what is our own major concern is to understand the thermodynamic analysis in an automobile engine, which serve as Otto cycle, which is the spark ignition cycle. The terminologies that we want to bring out of this, we are going to consider a piston cylinder arrangement, whereby we look at how the piston is moving. This thing is not new to each and every one of us, as the piston is moving in a to and fro motion. When it moves from down, which we know as the BBC, to move to the TDC, what happens to the volume occupied by the fuel? And what happens to the air? What happens to the two valves? There is a particular valve is called inlet valve, and the other one is called exhaust valve. So now let's pen down something. Figure 1 above illustrates a schematic and fundamental components of a reciprocating internal combustion engine, basically comprising a piston moving with a cylinder equipped with two valves. Despite its straightforward design, a piston cylinder device stands out as a remarkable versatile invention with an extensive broad of application. It serves as a powerhouse for majority of automobiles, trucks, light aircraft, ship, electric power generators, and various other devices. The piston reciprocates within the cylinder between two fixed positions, known as the top dead center (TDC) and the bottom dead center (BDC). The TDC represents the position of the piston when the cylinder has the smallest volume, while BDC denotes the position when the cylinder has the largest volume. Now, the maximum distance traveled by the piston in one direction That is, the distance that lies between the TDC and the BDC is termed as the stroke of the engine, while the diameter of the piston is referred to as the bore. The intake valve allows air or an air-fuel mixture into the cylinder, and the exhaust valve expels the combustion product. The minimum volume in that cylinder occurring when the piston is at TDC is termed the clearance volume. The volume swept out by the piston as it moves between TDC and BDC is called displacement volume. The compression ratio R of the engine is the ratio of the maximum volume in the cylinder to the minimum clearance volume. Now, the terminologies that we want us to be familiar with in this case in thermodynamics is the compression radius, which is defined as the distance moved at the BDC. R is the designated or denoted as the compression ratio. Is defined as the ratio of the volume at the BDC divided by the volume at what? CDC. And don't forget from what I just said earlier on that the distance that lies between BDC and TDC is known as what? The swept volume. Now, another term is the mechanical MEP. The MEP is referred to as mean effective pressure and is defined mathematically as MEP, mean effective pressure, is defined as the net work output divided by the maximum volume minus the minimum volume in the cylinder. This one is referred to as what? V max divided by what? V minimum. That is the compression ratio. Otto cycle analysis. The Otto cycle comprises of two processes. One occurs when work is being done and no heat is being transferred to the system. And the other ones occurs when heat is being transferred and no work is done into the system. Now we go back to the first law of thermodynamics, where we have change in U equals to change in Q plus change in W. Therefore, if we are analyzing state 2 to state 1, for example, we have U2 minus U1 equals to Q1 minus Q2 plus W1 minus W2. Now, let's consider the PV diagram and the TS diagram of Otto cycle. It is from that diagram that we are going to be analyzing the efficiency that we want to get out of the whole thing. Now we can start. We want to start analyzing. Following the first law expression that we have on the board, we want to start analyzing for different processes that we have. We have it from stage 1 to stage 4. Or we can call it process 1 to 2. Process 1 to 2, which is an isentropic process. And process 3 to 3, which is a constant isothermal. Process 3 to 4 is its what isentropic compression, then fall back to 1 is what an isothermal compression process. It comprises of two processes. You have two isochore and you have two isotherms. The two isotherms expands and compresses. The isochore, that one it is being supplied at a constant temperature as well as it is being rejected at a constant temperature. Now, for work inputs for stage 1 to stage 2 or process 1 to 2. Now, let's analyze for work inputs. Work input that is for W1 to 2 is taken as W work inputs equals to U2 minus U1. Don't forget, we said there are two processes in which work is being transferred and no it. So in this case, if we are analyzing for work, what happened to it? It escaped. So that is what we are trying to do here. For work input, we have it as U2 minus U1. And U is a function of specific heat at a constant volume and temperature. Don't forget, CV equals to what? Change in U over what? Over T. And change in U becomes what? CV. CV what? C. So which means U2 minus U1 becomes CV into bracket T2 minus T1. So U2 minus U1 in this case becomes what? CV into bracket T2 minus T1. So that is the work input. Now, for each input, that is Q1 to 2, which is the same thing as what happened at that level. Work is 0. So we have it as, or you go back to change in Q equals to change in W. So whatever you have at this level, you have it for Q at this level. Here for Q1 to 2 equals to what? U2 minus U1. And U equals to what? CV into bracket T2 minus T. At that level, we said there is no heat transfer at this level, 1 to 2. So what happened to the whole process? The whole process tends to 0. Now, for process 2 to 3, 2 to 3, this is where it is being added to the system. So this one is classified to as an isentropic process. Isentropic process. The process whereby Q tends to what? 0. Therefore, each input, looking at the diagram, you can see this is where it is being supplied to the system at stage 2 to 3. So Q2 to 3 equals to what? U3 minus U2, which is the same thing as CV. What happened at this level? You notice that the volume is constant at this level. Yes or no?
Yes, sir.
So CV into brackets what? T3 minus T2. So that is the heat input in this case. Then work output. The work output occurs at where? 3 to 4. It occurs at 3 to 4. So at this level, we have it as U3 minus U4, which is the same thing as CV into bracket T3 minus T4. So what happened at this level for Q? Q at this level tends to what? 0. Because it is what? An isentropic process. So the next thing is its output. The its output at this level is Q4 to 1. on 1, which is the same thing as U4 minus U1, which is the same thing as CV in bracket C4 minus what? C1. Now, the net work output. We can easily determine the net work output. The net work output equals to or work output minus work inputs. And work output is
CV.
W3 to 4, W3 to 4 minus W1 to 2, W1 to 2, which is given as what? 3 to 4 is
CV3 minus
CV into bracket C3 minus C4 minus CV into bracket what? C2
minus
T1. This is the net or the net work output. Alternatively, or the net work output equals to heat supply, which is heat inputs, Q inputs, whichever one that you want to use that of the two, minus
Q output.
Q outputs. And Q inputs is
Q2 to 3.
Q2 to 3 minus
Q4 to 1.
Q4 to 1, which is the same thing as Q2 to 3 is given as what?
CV3
CV into bracket C3 minus C2 minus CV into bracket C4 minus T1. So this can also be expressed as this. Now, what is the cycle efficiency? Don't forget, this cycle that we are analyzing, we want to look at the cycle efficiency. We want to get the Otto cycle efficiency. The cycle efficiency is net work output divided by what? Heat supply. Heat supply Q1, Q2 to 3. The net work output, everything is, we can take any one out of this, CV into bracket, or we can take this, let's take this, CV into bracket, C3 minus C2 minus CV into bracket, C4 minus T1 divided by 2 to 3. CV into bracket what? T3 minus T2. Something is wrong now.
Yeah.
Alright. So the cycle efficiency becomes 1 minus C4 minus T1 over what? T3 minus T2. We are not yet done. This is where we will now apply some forms of thermodynamic mathematical expression. For process 1 to 2 and process 3 to 4, they are isentropic process. Isentropic expansion and isentropic compression. So what happens to the volume at that level? V2 equals to what? V3. And V1 equals to V4. This is it. Now, let's look at the isentropic compression process. For isentropic compression process, T2 over T1 equals to V1 over V2 raised to the power of gamma minus 1. And note that we have defined the compression ratio as V1 over V2. We define it as compression ratio. So we can use V1 over V2 as R. T2 over T1 equals to compression ratio raised to the power of gamma minus 1. Now make T2 the subject of the formula in this case. T2 becomes T1 multiplied by the compression ratio raised to the power of gamma minus 1. You can name this as equation 1, which we are going to need later. Then also, for the isentropic expansion process, this is isentropic compression process. So, isentropic expansion process, we have T4 over T3 equals to B3 over what? B4 raised to the power of gamma minus 1. So at this level, we make T3 the subject of the formula. This gentleman becomes expansion ratio. This one is called compression ratio because it compresses at this level, it expands at this level. So we have T4 over T3 equals to R expansion raised to the power of gamma minus 1. Therefore, T3 equals to T4 multiplied by gamma expansion raised to the power of gamma minus 1. We name this as equation 2. Now, from the cycle efficiency, which we have already calculated earlier on as 1 minus T4 minus T1
over
divided by T3 minus T2. So what we want to do now is this. We want the numerator expression to be the same thing as the denominator expression. We make T2 the subject of the formula in this case. So wherever we set our eyes on T2, we represent it as T1 so that it can fall in the same category. Then also, wherever we set our eyes on T3, we represent it with what? T4. So now, let's substitute this. 1 minus T4 minus T1 divided by T3 is T4 into bracket the expansion ratio raised to the power of what? Gamma minus 1 minus T2 T1 compression ratio raised to the power of gamma minus 1. So something is common here. 1 minus T4 minus T1 divided by gamma minus 1 is common. Yes or no?
Yes, sir.
So we have T4 minus T1 raised to the power of what? Compression ratio raised to the power of what? Gamma minus 1. I don't know whether I'm making sense.
Yes.
So something can go. This gentleman can cancel out. So the thermal efficiency now becomes 1 minus 1 over the compression ratio raised to the power of gamma minus 1. So this is the Otto cycle efficiency. Note that R is defined as compression ratio, is the volume at BDC divided by the volume at what? TDC. Which is also the same thing as the maximum volume divided by the minimum volume. Then also gamma is known as the specific ratio, which is given as Cp over what? Cp. And for air, its value is given as 1.4.